Welcome to the course on advanced power electronics. Today we'll cover synchronous reluctance motor drive. So outline of the presentation, type of application of synchronous reluctance motor. We'll cover of course introduction and history development, then operating principle of synchronous motor drive, control of synchronous motor drive, case study of synchronous motor drive, the control of synchronous reluctance motor drive for solar pumping, and speed sensorless control of synchronous reluctance motor for electric vehicle applications, solved numerical problems and references. So these typically you can think about the latest trend of the synchronous reluctance motor, how it look like, and you can see the photograph as well as you can see the cutway, how the typically and the really from the animation you can see how it really rotate, like when you excite the three-phase winding of stator by three-phase currents. So here we have a very interesting arrangement that we have a stator with the winding similar to like induction or typically power magnet synchronous motor. In the rotor only we have a CLNC with a flux barrier. However, the rotor is a smooth, it's only cut portion of the rotor with the segmental kind of arrangement, and because of this reason we get a good CLNC around 8 to 10 LD upon LQ. Apart from that, there is one more advantage that it can even run at very high speed. So it's not a kind of projecting kind of force which normally synchronous reluctance motor is there. So you can just see typically how the synchronous reluctance motor there, the rotor, the rotor as unassembled motor from the side view, as well as the kind of animation and the different segments of these motors, and typically the assembled motor kind of. Now these are the different parts, with the labels in this, and where all these labels are defined in this neck, the different parts of exploded view of this synchronous reluctance motor, including the typically all the parts. Then you can say synchronous reluctance motor has the same structure as that of a silent pole synchronous motor, except that it does not have a field winding on the rotor. It's only a ferromagnetic structure with the, you can call it the flux barriers. So speed is controlled by controlling the voltage and stator voltage and frequency, because we have only winding on the stator, normally three-phase winding, provided if we want to go some special motor maybe more than three-phase. It has a zero slip because synchronous operation without the magnet, and configuration as depicted here has no starting cage, so it run only by inverter power. And of course you can see the different parts like how the silent pole rotor, how the stator core, how the stator winding, and typical reluctance motor cross section area. You can see the typical kind of couple of animation. A typical synchronous reluctance motor, how to run with the cross section. So you can see on the left side as well as on the right side two kind of animation. When you excite three-phase winding from the stator side, how the rotor really get locked at synchronous speed, and the rotor speed decided by, of course, the number of poles as well as your frequency of excitation. Majority of the motor nowadays which are driven by inverter are 4-pole. In 4-pole you get a very better symmetry. In that case. However, these motors with the inverter run by at 3000 RPM from the same rated voltage, so that flux is reduced and you don't have a typically the large magnetizing current, because this is one of the major drawback of large magnetizing current in this motor. So now coming no magnets, what are that one? No magnet, no skulkage, no juice losses in the rotor, similar stator as induction motor, same power frame ratio as induction motor, require electronics controller or inverter, and of course it has a little higher current than low power factor power. But if you design with the power flux control, then these drawback can be eliminated by even simple control. So you can just see how really it goes with the power magnet synchronous motor or induction motor, and how this synchronous reluctance motor is there as a comparison, which does not have a cage, no winding, and no magnet on the rotor. So now recently synchronous reluctance motor has a subject of interest for many variable speed industrial application. So there are no winding, magnets or cages in the rotor. The rotor of synchronous reluctance motor are cheaper and lighter than the rotor of induction machine and power magnet synchronous machine with same size, and the rotor temperature is very low, and the torque ampere ratio is independent of rotor temperature, unlike that of both induction motor and power magnet synchronous motor. And the stator of synchronous reluctance motor and the inverter to supply them are identical to those of both induction motor and power magnet synchronous motor. So the speed control without encoder or sensorless is much easier owing to the anisotropy of the rotor design, and power factor of synchronous reluctance is poor compared to both induction and PCM, requiring a little higher inverter rating. But if you really proper control the flux according to the load requirement, this drawback also can be eliminated, and you can increase the efficiency of the whole drive. So efficiency of synchronous reluctance motor is much better than of induction motor and is inferior to that of PMSM of the same power rating. And recent synchronous reluctance motors, an amount of low cost permanganate ferrite is also inserted in the rotor to further improve the torque density and power factor, and this machine called permanganate assisted synchronous reluctance motor. So, well, the basic features are distributed winding on stator similar to induction motor, and synchronous reluctance motor have a with flux barrier for maximization of magnetic and isotropic, like LD is not equal to LQ. And these are the typical photograph. You can see the cutway of the typically the open axis of this motor, and typically the laminations of the rotor and different parts as typical photograph. So now coming to the application of this synchronous reluctance motor. Is used in pumps and conveyor for proportionally devices and in synthetic fiber manufacturing industry, and for positioning of control rods in nuclear reactor, and in synchronized textile drives, and in wrapping and folding machines, and for processing of continuous seed or film material, and in constant speed applications such as recording instrument, the control apparatus, regulators, time devices, phonograph, turntable, and so on. And of course, coming to the metering application, you can see how it look like metering application. Then the wrapping and folding machines. The major reason for this is it runs with the variable frequency drive, and there is no losses in the rotor. It increases the efficiency much higher than what we really use for in induction motor. Apart from that, we control the flux also, so that the your power factor also improved to reduce the kVA requirement from the inverter. So now another is the synthetic fiber manufacturing equipment, where of course in these applications you need a very precise speed and position control. Apart from that, you have a load varying. So when you have a load varying, you have easily either vector control or direct control to control the flux in much better manner. Like, and then pressure booster pump, where we use this. Then the pumps and conveyor. So in pumps it is very popular. Even people are replacing the induction motor by this synchronous reluctance motor, because with proper design it increases the efficiency 4 to 5%, and the payback is hardly a couple of years for investing the even new motor of this kind in these applications. The electric vehicle also, because it's a brushless motor, has a higher efficiency than induction motor, and there is no danger of the magnets to demagnetize, so it's becoming popular for electric vehicle also. Like, this example is typically a Lucas chloride, then the Tesla, then the typically another model, where this new kind of these motors are used also. And of course, this is typical synchronous motor drive up typically with the rating for electric vehicle, and the comparison with the synchronous reluctance if you use in place of prior existing motor like also. So it has a certainly little higher weight, but magnets are not there. Like here. So now coming to history and development. So we started this synchronous reluctance machine, simple silent pole structure, projecting pole, as you can see. Then the people have in induction motor itself on the rotor of cage bar, we will remove some portion, as you can see, top to geometry, remove some portion of this. So we call it like a typically again projecting kind of poles. And then we have a segmental structure followed by IPM based structure from where we don't put the magnet, and the double barrier structure. And this is how really the development from 1888 to typically 1923, then 1960, 1999, and then of course the big industry like you can call it ABB start manufacturing this synchronous reluctance motor for servo motor applications, position control. It's a synchronous motor which can be precisely controlled. And then of course recently around 2000, you can call it 10, they have come for general purpose applications, which really we talk about pump also, because of hardly higher efficiency with the die package. Then this is the concept which was given Costco in polyphase reaction synchronous motor through a paper American Institute of Electrical in 1923 about the concept of flux barrier, and then Vagati filed the patent in synchronous reluctance motor having a low torque ripple design in 1998 with the similar kind of flux barrier, which is very popular today, like for variable speed. So starting with the development of history of the rotor, as you can see with the typically with the cage bars here, because we were running with the supply, so we need the starting torque as an induction motor. During starting, the cage bar is required for that. The rotor is replaced by a cage rotor, and the cage causes a reduction in the saliency ratio, which yields to impair the power factor and efficiency of the motor comparing the cageless one. The motor had poor performance comparing with the other alternating current machines and cross-section of synchronous motor with cage windings in the rotor. By removing the teeth from the rotor of a conventional induction motor, the saliency can be achieved. The saliency ratio eta, we call it LD upon LQ, is normally less than 3 in that case. So you can see how really it looks like a cross section of synchronous reluctance motor design by modifying the rotor of traditional induction motor. Then the rotor of an ordinary silent pole synchronous motor without the excitation, and the saliency ratio is still low. The saliency ratio for this rotor geometry also was reported around 3, which shows the cross section of synchronous reluctance by removing the excitation winding from the silent pole synchronous motor. Then rotor with flux barrier. So by adding a flux barrier of a non-magnetic material in the Q axis below the cage winding, the rotor saliency was achieved, and this geometry allowed the motor to start direct online. This was actually you can call it the silent pole synchronous, but you can call it line start because cage barriers are there. So cross section of layer flux barrier geometry by adding flux barriers below the cage winding, and then by removing the permanganate from the interior permanganate motor, the flux barriers insulation is achieved, and the saliency ratio of this kind of geometry was reported around 6 to 8. So just removing the permanganate from the interior permanganate motor like. Then of course you can call it in 1923 Kostoko investigated the aforementioned rotor geometry is mainly due to the faulty form of the rotor, and to increase the torque it is necessary to prevent as much as possible the formation of transverse field. To cut out that part of the rotor where Q axis field will be maximum, in these rotor designs some of the usual D axis field are lost. So this is typically cross section of transversely laminated anisotropic type TLA construction type. Then another reported later on the axially, you can call it laminated anisotropic rotor called ALA. As you can see in the photograph also it look like. So laminations are probably shaped insulated to each other by magnetically and electronically passive material, and stakes are connecting through the pole holder to the central part of the where the shaft is connected. This is a cross section of the axially laminated anisotropic rotor. Now this is transversely laminated anisotropic rotor which is finally today. The laminations are punched in the traditional way. Thin ribs are left to hold the rotor segment together. To achieve the anisotropy, these ribs should be magnetically saturated, results an additional leakage component in the Q axis flux, and TLA rotor gives the mechanical strength to rotor stack in an easy and cheap way. And saliency ratio, the saliency ratio TLA has lower than the ALA. You can see the cross section of the TLA rotor with equal space between the equivalent rotor slots. And these are, of course, you can call it the type of rotors. Possible rotor design for synchronous reluctance motor, simple silent pole, then how it going to institute axially laminated anisotropy, and then the transversely laminated rotor like. And you can see how segmental type, typically with the flux barrier, and how the ALA type, and typically high anisotropic rotor structure with axially and transversely laminations of two kinds with the flux barrier. Now coming to advantages of this synchronous reluctance motor, it has a higher efficiency, no conduction losses in the rotor, it generates the less heat and has a less maintenance due to the lower bearing temperature and rotor synchronicity, granting a more accurate speed control, no rotor slip, and higher torque density, and lower rotor inertia means faster torque dynamics. And disadvantages are slightly lower power factor for potentially increase inverter requirement, higher cost than induction motor, need speed synchronization to inverter output frequency by using rotor position sensor and sensorless control, and not widely manufactured or available yet. So coming to comparison of synchronous reluctance with the other two motors, typically comparison of synchronous reluctance motor with the induction motor. So left side, typically you can say left side kind of induction motor, on right side you can see the synchronous reluctance motor with the elimination of resistive rotor losses. And then you can see typically comparison here. You can see in this geometry, I mean, inside is the synchronous and outside is the induction motor, which it looks to be like a white. So you can see the for same power rating, how is the geometry there. So here, I mean, you can have a typically IE3 compact design without compromising efficiency. It has a full range, verified package efficiency, induction motor on the outside, innovative inside, and same size motor, higher power, or you can say same power, smaller motor. And you can see the schematic and comparison bit of the rotor geometry of synchronous reluctance motor on left side in A and induction motor on right side. Now comparison with a powerful, typically you can see how it looks like. So powerful yet highly compact motor up to 2 frame sizes is smaller than the conventional motor, and variant codes and mechanical construction based on the proven M3BP cast iron process performance motor, and no magnets, no cage, and competitive product offering compared to the traditional or other new technology, and higher reliability through the lower bearing temperature and higher efficiency than the conventional variable speed drive fed induction motor. And here you can see comparison. So here we have a I2 induction motor where you have a total losses, let's say we call it 100%. So here if we say if we take a typically a motor with the higher output, then we can get a typically the losses 80 to 90%. And if we take IE4 motor, the losses are reduced from your 100% to typically only 60%. So certainly if losses are reduced by 40%, your efficiency certainly improved drastically in case of synchronous reluctance motor. And you can just see here efficiency comparison of synchronous and induction motor. Lower side is the induction motor, higher side the synchronous motor, and you will find this difference in efficiency. I mean, in lower rating. Lower rating is a big margin in the improvement in efficiency of synchronous reluctance motor. So that's the reason people are suggesting for lower rating for many applications, including like a solar watt pumping or normal pumping with the inverter fed drive, that we should use the synchronous reluctance motor for lower rating. I mean, for many applications, for typically for water pumping or many other kind of pumping like a liquid pumping in the typically milk dairies as well as the oil industry, refineries, and many places. The use of synchronous reluctance motor technology ensures a noticeable lower energy consumption in all load range. And cross section is synchronous with the outer typically rotor, how it look like, and cross section of 2-pole external rotor. I mean, you have external rotor also many applications, so that's kind of geometry like. And you can see the compared to permanent synchronous motor, how the synchronous reluctance motor look like with the typically like a plug barrier clearly. So this is table 1 of a steady state operation synchronous and permanent reluctance motor. So here you can just see clearly of 250 RPM and 500 RPM for different torques, that how the typically the power factor and efficiency, I mean, like are there in reluctance motor and the typically. So you can just see we get typically in this motor also we get quite, I mean, reasonably not much inferior performance. I mean, as far as typically you can call it efficiency requirement is concerned. And this is, you can call it comparison of synchronous with other motors compared to your reluctance based PMSM. If you say the geometry, then synchronous reluctance motor, then induction, wound rotor, synchronous, then RE free permanent synchronous and switch reluctance motor. So you can just see clearly how really the typical, so same rating, that what the performance wise, efficiency wise, motor cost wise, inverter cost wise, reverse furnace, installed torque manufacturing, and VH recycled and maximum power at maximum speed correspondingly. So coming to synchronous motor, reducing the losses up to 40%, which you all talk about I4. I mean, like if you take a traditional I2 induction motor and you take I4 synchronous reluctance, which is available nowadays, the loss are in induction motor if it's 100%, then in this synchronous reluctance motor it reduces to 60%, which rotor losses are completely eliminated, like especially the electrical losses on the rotor. Like, and this is the key success for elimination of rotor losses, as we talked about earlier also, compared to I2 induction motor, how we in I4 were able to reduce the losses about 40%, and we saw the efficiency also improvement drastically, especially on lower power rating. So this is a comparison, I mean, typically caused by the bound at highest, induction motor moderate, but synchronous reluctance motor have a low, because you don't have even a copper or aluminum on the rotor here. Power density, PMSM high, so of course it's comparable to induction motor. Efficiency also moderate, and noise and vibration also of course have a challenge, but it's improved now, and manufacturing of course easy here. And these are the typically you can call it the advantage and disadvantage of these all induction surface PM interior palm magnet and reluctance and synchronous reluctance motor. So synchronous silent pole without magnets and simple control, and lower power of course hard to design with the flux variant. So coming to like a rotor of synchronous reluctance motor are cheaper and light than the rotors of induction machine and palm magnet synchronous machine with the same size, and the power factor of synchronous reluctance motor is rather poor compared to the both induction motor and palm magnet synchronous motor, and the efficiency of synchronous motor is much better than that of induction motor and is inferior to that of palm magnet synchronous machine. And the stators of synchronous reluctance motor and the inverter to supply them are identical to both of those of both induction and PM machine. Now coming to typically types of rotor in synchronous reluctance motor. So we already talked about 3 types of synchronous reluctance motor with an isotropic rotor structure: simple silent pole rotor, then axially limited rotor, and transversely typically laminated rotor. And starting with the typically the silent pole rotor, as the first possibility is made by removing some iron metal from each rotor in the transverse. Again, as you can see, 4-pole conventional silent pole design, and this was the axially laminated. So in axially laminated rotor, the laminations iron are suitably shaped at each pole and insulated from each other using electronically and magnetically passive material insulation, and the resulting stacks are connected through the pole holders to the center region to which the shaft is connected. And you can say simple pole 4-pole axially limited rotor design. And coming to mostly employed today is a transversely laminated rotor. So in the third type of the rotor, the laminations are punched in a traditional way, and thin ribs are left while punching. The various rotor segments are connected to each other by these ribs, and you can say rotor is quite typically on the air gap rotor is quite smooth. You can run at very high speed also. You can say here the highly anisotropic rotor structure with axially and transversely lamination, and you can just see how the multiple flux barrier, in case of 4-pole motor, typically conventional, and how axially limited anisotropic rotor typically. And here you can say normally the conventional limiter LD upon LQ is less than 3 for low power factor 0.45, and higher peripheral speed are acceptable. So here you can say in typically LD upon LQ is 4 to 8 with the multiple flux barrier. LD upon LQ is greater than 8 to 10 in ALA construction, and in conventional LD upon LQ is order of 2 to 3 only. And you can say multiple layer internal flux barriers rotor for different power rating. If 9 kilowatt you can see, then the typically 42 kilowatt we have higher than 110. We have of course less number of this kind, and in case of 40 kilowatt we have a many flux barrier around. Typically you can say 7 flux barrier if you see on the right side. And you can say here how your design concept typically in these motors. So single, you can seat of the punch electrical sheet. The seats is stacked to complete. Rotor body can either be stacked or pre-assembly piece or direct on the shaft, and mounting the rotor body on the shaft, the rotor will be balanced after shaft assembly. And the typically rotor body insert in a stator, a standard stator of 4-pole design is used, but with the adapted winding. And these are the typically the rotor stack of laminations of, you can see with the typical photograph and how it is get assembled typically with the typically the 3 flux barrier as well as your 5 flux barrier. And then you can say how the synchronous reluctance motor with double layer stator winding, then V-shape stator without winding or PM stator winding, and the double layer rotor with PM permanent. You can, and then V-shape stator without permanent and PM without rotor without permanent. So you can see as many like a typically 5 flux barrier on the in F. These are without permanent material and with permanent material. Because this geometry originally came after long iteration from the permanent synchronous motor which are used in electric vehicle. The synchronous reluctance motor also new kind of is offshoot of that only. So you can say 4-pole transversely limited. So when the PMs are inserted into the rotor flux barrier of a synchronous reluctance motor, it becomes a permanent assisted synchronous reluctance motor, and permanents can be mounted in the rotor core of the axially or transversely laminated structure, and the polarity of magnets is chosen such that the counteract the Q axis of the synchronous motor at the rated load. Now coming to working and operating principle of synchronous reluctance motor. You can just see how the typically your flux line and how the rotor is at the power angle delta, and how the torque is developed, and how the D and Q axis are defined. And you have a torque develop also T equal to 3 by 2 pp in bracket 1 upon LQ minus 1 upon LD phi square sine 2 delta, where P is the number of pole pairs in the motor of this kind as a basic principle. Now coming to operating principle, the reluctance concept in which the rotor rotates due to flux variation in order to fulfill the maximum reluctance path. An isotropic rotor is placed in a magnetic field with a definite direction. The reluctance torque is produced, and this torque is due to the interaction of the non-uniform magnetic reluctance in both D and Q axis of the anisotropic rotor and the magnetic field, and so torque is developed independent on the difference of LD and LQ for certain stator current, and a key parameter is saliency ratio, which is equal to LD upon LQ. So now characteristic of this synchronous reluctance motor: the synchronous motor is not of self-starting without the skull cage, and during run-up it behaves as an induction motor, but which approaches synchronous speed, the reluctance torque takes over and the motor locks in synchronous speed. And this is typically the direct fluxes of air gap flux in a 7-pole synchronous reluctance machine, how it look like, how with the geometry it is there, and how typically, let's say, the third harmonics and typically quadrature axis fluxes in 7-pole the synchronous reluctance motor. Now coming to importance of your saliency ratio, the performance parameter dependent on saliency ratio is power factor, efficiency, torque density, and speed range at constant power. So you can just see how the high reluctance magnetic circuit is there with the, you can say, with the flux moving, and low reluctance magnet in dark color is shown in operating. So this reluctance motor operates according to the principle of magnetic reluctance, and the rotor consisting of air and iron has the least possible magnetic reluctance in the one direction and the highest possible reluctance in the direction perpendicular to that. And because the system always moves towards the lower magnetic reluctance, rotational movement results. And you can see how the typically excitation of the axis magnetic maximum permeance axis and excitation of maximum reluctance axis. And you can say crossing of an isotropic rotor placed in the magnetic field, with the, of course, with the power angle delta, you can say, and how the D and Q axis are defined on the right side, like in two positions, and how the typically the crossing of an isotropic rotor placed in a magnetic field, like in the basic stator rotor structure. Like it's a basic principle how the rotor is there. Typically in the D axis, and how the your field winding is typically the armature winding on the stator corresponding group or two work. Coming to equivalent circuits, so we have a equivalent circuit according to the stator stationary reference frame. Where you have a typically your resistance, inductance, and then you have a back EMF and the magnetizing component and the core loss component, as well as the damper bars and all that, and that is equivalent in the. So we can say here the IS is the amplitude of stator current vector, RS is resistance, winding resistance, lambda is amplitude of stator flux linkage, and LS delta LM is the stator leakage and the magnetizing inductance per phase, and LS lambda is leakage plus magnetizing and flux, and the simplified equivalent circuit according to the stator stationary reference frame. And this is equivalent circuit according to synchronous reference frame. So in synchronous reference frame, you just see that we have a typically the back EMF, resistance, back EMF, inductance, and magnetizing inductance. So coming to stator terminal voltage vector in stationary reference frame given as Vs equal to Rs IS plus d lambda S upon dt. The lambda S is L delta plus Lm into Is, that is lambda S delta plus lambda m, and Vs equal to Vd plus jVq, and Is equal to Id plus j iq, and lambda is equal to lambda sd plus j lambda sq. And voltage equation is written here: Vd equal to RSID plus d lambda sd upon dt minus omega me minus into lambda sq, and vq equal to rs iq plus d lambda c sq dt minus omega me into lambda sd. Let's say speed voltage actually, or like so where omega m is the electrical angular velocity, angular speed of the motor, and lambda sd and sq are the flux linkage component in d and q axis direction. Lambda sd equal to lambda md plus lambda s delta d equal to lambda md plus lmd plus ls lambda into id equal to ld iq, and lambda sq equal to lambda mq plus lambda s delta q, and in bracket lmq plus l delta into iq, that is lq iq. Now coming to phasor diagrams of the synchronous motor, so you can say here the vector diagram of with nominal operating condition, where you have a q a axis and you have a d axis and q axis. Of course, they are rotating at synchronous speed. So you have a typical, and you have a like a typically flux corresponding to the power angle, when defining the total flux. Then you have a direct axis flux, then the leakage flux, which is summation of these two. And similarly, you can see the stator current, as well as the typical q axis current and voltage. So you have a certain lagging power factor, so current is supply current lagging with that, but you have a component of d and q. So coming to like now from the vector diagram, the load angle can be computed as delta equal to tan inverse lambda sq upon lambda sd, and tan inverse ld lq iq upon ld id equal to tan inverse your 1 upon eta iq upon id. And of course, the current angle can be computed from id iq as alpha I electrical equal to tan inverse iq upon id, and thus the load angle is defined delta equal to tan inverse 1 upon eta tan alpha e, or tan delta equal to 1 upon eta tan alpha e. So both your delta and alpha have effect on the machine performance as well as the saliency ratio eta. Now coming to electromagnetic torque, from the interaction between the stator current vector and the flux linkage vector, the magnetic torque is T equal to 3 by 2 P lambda s into cross is, and where the P number of pole pair, that is T equal to 3 by 2 P in bracket lambda s d iq minus lambda s sq id equal to 3 by 2 in bracket lambda s d I lambda s d lambda q minus lambda d upon ld equal to 3 by 2 P lambda sd into lambda sd in bracket 1 upon lq minus 1 upon ld. So now by substituting lambda is equal to Vs upon omega me, the electromagnetic torque can be expressed as a function of the motor saliency, the amplitude of the stator voltage space vector Vs, and the load angle as T equal to 3 by 2 P lambda s square in bracket ld minus lq upon ld lq cos delta sin delta equal to 3 by 2 P lambda s square in bracket ld minus lq upon 2 ld lq sin 2 delta, and equal to 3 by 2 P Vs square in bracket ld minus lq upon 2 omega m square ld lq into sin 2 delta. And the electromagnetic torque can be expressed as a function of the motor saliency, the amplitude of the stator current space vector is, and the current angle as T equal to 3 by 2 P in bracket ld minus lq into id iq equal to 3 by 2 P by 2 then ld minus lq ic square sin 2 alpha I. And this is typically, like you can say, electromagnetic torque versus load angle at different saliency ratio. So as you increase the saliency ratio, you can say how the torque varies. Like, so you may find that you get a reasonably good torque at the saliency ratio of around 10. Like is not much different than the saliency of 15 as well as 50. So people conclude that the best saliency ratio is around typically order of 10. And this is typically the torque with the different saliency ratio, electromagnetic torque versus your current angle at different saliency ratio. So the power factor cos phi can be computed as cos phi equal to cos in bracket pi by 2 minus alpha I minus plus delta. And by neglecting stator resistive losses and iron loss, it's possible to express the balance of electromagnetic energy and conversion 3 by 2 PVS cos pi equal to T omega m, and where lambda is under root or lambda q square, lambda d square plus lambda q square, and I is equal to under root id square plus iq square, and cos phi equal to ld minus lq id iq divided by under root ld id square plus lq iq square into under root id square plus iq square. and then cos phi equal to LQ eta minus 1 ID IQ divided by LD LQ under root LD ID divided by LQ IQ square plus 1 under root ID square plus IQ square and in equal to eta minus 1 ID upon under root ID square plus IQ square divided by under root eta upon tan alpha I square plus 1 or equal to then eta minus 1 cos alpha I divided by under root eta square in bracket cos alpha square divided by sin square Li plus 1 and equal to eta minus 1 cos alpha divided by under root eta square 1 upon sin square alpha I plus 1 upon sin square alpha I. So that is eta minus 1 under root sin 2 alpha I divided by 2 tan alpha I plus eta square cot alpha I. And this is typically the, you can call it the power factor or the synchronous lambda as a function of current angle. So here you can say the power factor, you are able to get quite good power factor again, the saliency ratio of order of 10 like. And then the power factor with your saliency ratio would really vary. So here also you are able to get the good power factor of 0.8 around at the saliency of 8, around 8 to 10. And this is operating limits of working points. I mean, you have a typically maximum torque per volt ampere and then the maximum torque per maximum ampere. And all these characteristics are shown here for the different speed because you control the speed and how the torque there like. So now coming to operating limits, working points, the electromagnetic torque operating region should be within the voltage and current limit of the motor, and the voltage limit depends on the winding insulation limit. The maximum current is based on the thermal limit, which depends on the huge cooling system. And to study the operating regions of the reluctance motor, the steady state condition is assumed. And now coming to voltage limit, the voltage and current limit in the synchronous reluctance motor are expressed as UD square plus UP square. That is typically we can call it like a equal to U1 square or U1 equal to under root 2 by 3 U nominal, and the amplitude of stator voltage vector here, and by neglecting the stator resistance, the expression for UD UP at steady state condition UD equal to minus omega me LD LQ IQ and UQ equal to omega me LD into ID. The voltage limit can be expressed as function of the stator current as in bracket omega me LQ IQ square plus omega me LD ID square less than U1 square. So the current limit is IN equal to root 2 I nominal is the amplitude of stator current. Space factor for all values should be phase voltage and currents ID square plus I square less than IN square. The current limit is presented as a circle with radius equal to IN, and the voltage limit is reached at the base speed omega b, that is presented as its eclipse, and the torque log V in the synchronous rotating frame is presented by the family of hyperbolas with the asymptotic torques located in the D and Q axis. And this typically you can call it characteristic maximum torque per ampere at Tn, and then after that we go to your field weakening zone region 2, and then we go for maximum torque per volt region 3. Like for many applications this becomes important. So synchronous motor run in 3 different control regions. Follow region 1 constant torque region. So below the base speed omega b, it is possible to produce the maximum torque, certifying the voltage and current constant by applying MTPA control, and maximum available your torque obtained by MTPA control Tn is achieved at the base speed and the torque hyperbolic tangent to the current circle limit at the point B in the figure. The base speed can be computed as omega b equal to root 2 U1 divided by IN under root LD square plus LQ square. So coming to region 2 constant volt ampere region, that's called field weakening, flux weakening region. So above the base speed, the current vector controlled by flux weakening control, the voltage is kept constant and the speed increases according to V equal to omega me into lambda. The flux is reduced by increasing the current angle. The D axis current is reduced and the Q axis current is increased. So the flux linkage in both D and Q axis are changed due to the change of ID and IQ, and the reduction of flux linkage lambda D is more than the increase in the of the lambda Q, and by changing the current angle, the current vector trajectory move along with the current limit circle up to speed omega b there. So region 3 Further decreasing the volt ampere region, flux weakening region. So from the above figure, the motor speed omega b dash is achieved when the current limited circle is intersect with your maximum torque per volt stage, and thus for speed above the omega b dash, the optimum current vector is achieved by applying the MTP control as shown in the figure. Now coming to control algorithms of synchronous reluctance motor drive. So coming to scalar control of synchronous reluctance motor drive, the scalar control of synchronous reluctance motor can be through synchronous reluctance mode and self-control mode both. And one traditionally popular application of synchronous mode is a true synchronous mode in the multi-motor drive by open loop V/F control. And with the V/F control, the motor requires temper winding to prevent hunting or oscillations during the load tangent. And these are typically a diagram of scalar control. So we have a typically the battery with buck boost converter, and we are controlling the typically the frequency reference there with the frequency, and then we are going flux control then switching circuit with the input as voltage. So this we give to the gating signal of this boost converter. And topology for true synchronous mode, we have again here battery with the buck boost converter. So we take a feedback here. With the delay circuit and current controller, we form frequency. We just calculate the rise of frequency, then corresponding voltage, and we give switching circuit for your duty cycle as well as voltage and frequency to the inverter. And this is the matrix converter for drive. So we have frequency with certainly with the delay rise, and then the voltage corresponding to that, and we have a voltage versus getting, let's say, angle, and that given to the band, typically matrix-driven matrix converter. Coming to for self-control mode, so voltage here we are in self-control mode. We have a battery again buck boost converter. So what we have with the sensor, we have a speed, and that is speed is compared with the reference speed, and that error converted to the power angle, that's a burst R, and from omega R we are able to get typically the frequency and voltage, which is given to the switching logic along with the delta test, and that feeds the inverter. And coming to like typical self-controlled in matrix converter base, so here we have again encoder on which you get the speed to current and then from angle we get sin theta and cosine theta. Go to controller to have a three-phase UAU UCC, we have a peak of amplitude of the current multiplied the three-phase template which goes to as a three-phase reference current. With the duty cycle control, we control the switching of the matrix converter. Now coming to vector control of synchronous reluctance mode drive. So we can say torque of a synchronous reluctance motor is given by T equal to 3P by 2 in bracket LD minus LQ into IDIQ. So the values of LD equal to LDM plus LS and LQ equal to LQM LS, where LD LQ are the typically magnetizing inductance along with DQ axis respectively, and LS is the leakage your inductance. In the conventional reluctance motor with the ratio LDM upon LQM lies between 2.5 to 4, which is improved the range of 10 to 23 with flux barrier in the rotor. So however, with the axially laminated and tropic struck rotor, this ratio is increased to very high value, and this increases the torque capability of the motor. So stator current is given IS dash equal to ID plus JIQ equal to IS into e to power J theta R and equal to I alpha plus I beta into e to power minus J theta R. So now there are two criteria for control of synchronous reluctance motor: the maximum torque per flux. So in this criteria, the flux is given by lambda max T equal to 4 T star LD LQ upon 3P LD minus LQ to power half, and the current is ID star equal to lambda MT maximum T divided by root 2 into LD for the omega speed below the base speed. So maximum power factor, for maximum power factor, the flux shall be lambda P max equal to under root bracket 2T star in bracket LD square plus LD LQ bracket close LD upon LQ to power half, and by 3 P into LD minus LQ, and the current ID star equal to your lambda max PF divided by under root 2 LD into omega base divided by omega below the base for speed. The Q axis reference current in both the cases can be calculated by the relation derived from the torque equation as IQ star equal to 2T upon 3P into LD minus LQ into ID star. And this is the vector control diagram of your synchronous reluctance motor drive. So we are setting the position from the rotor, and we are estimating the speed by derivative of it. And this is reference speed with your estimated speed goes to the speed control, which gives the torque reference. And with the speed and torque, we are able to get IDIQ. And then from sense current, from using a Clark and Park transformer, we get IDIQ. And we have a current controller, which output is given VDQ. And we have a typically the inverse Park transformation, which gives V alpha beta. Then we use the inverse Clark transformation to get the your, let's say, three-phase voltage VBVC, which given to duty cycle control of VSI. And of course, here we have a typically a battery with the buck boost converter for this application. Another is VSI fed current control. So here also again we have an encoder to get the position, from position the speed, then the reference speed is there, then speed controller. Then we go to, of course, with the speed and torque to vector control, we calculate IDIQ, and with the sense current, then we go to the Clark and Park transformation to get IDIQ, and then we go to current control with VDBQ, we use the inverse Park transformation to get a with the theta your V alpha beta, and then that we convert from inverse Clark transformation to get VABVC for duty cycle control of this matrix converter. Then this is typically vector control synchronous motor drive with the matrix converter synchronous voltage control fed. So we have again encoder, reference speed, and then we get the speed control torque, and then we have a from position current reference. Then with the position we get Clark and Park transformation to get three-phase current, and then we have a sense current, so we have a current control for this VSI. So another is the direct torque control of the synchronous motor drive. So in DTC, torque and flux have to be estimated using the following relation. So flux is lambda equal to lambda D plus J lambda Q, where lambda D equal to LD LID and lambda Q is LQ IQ. Torque is T equal to 3P by 2. Lambda D minus lambda Q into ID IQ. However, the position theta R estimation had to be accurate. This can be done by encoder or resolver, and various topology applied earlier can also be applied to the direct torque control of synchronous reluctance motor. So this is typically the direct torque control of synchronous reluctance motor of battery fed your with the voltage source inverter fed synchronous reluctance drive. So we have a position sensor. From position we get the speed, we have a speed control, give the torque, and from actual speed we get the flux reference. So flux reference and this we have from the current, and typically from the position we are able to get the flux and the torque estimation. So we go to two level and 3 level flux and torque controller, which with the sector we go for table of optimal switching to give the gating signal for the voltage source inverter driving the synchronous reluctance motor. So in case of DTC of synchronous reluctance motor drive, the error in flux vector have 3 distinct possibilities. If the flux lambda is greater than flux in lambda star, it is taken as -1 in the table of optimal switching. If lambda star by 2 is in between lambda and lambda star, so it is taken as 0 in the table of optimal switching. If the lambda is less than lambda star by √2, it is taken as a 1 in table of 10. So sliding mode control is considered suitable as a speed control because it directly produces bipositional output T plus and T minus. So switching function can be as S equal to omega r star minus omega r minus T d omega r upon dt, and the torque control I shall be T plus T star for S greater than 1 and for minus T star for S less than 0. And this is the table of optimal switching. We have a 3 level flux and 2 level torque. You can see here, and the different sectors with theta 1, theta 2, and these are the voltage vector V0 to V7. V0 and V7 are 0 vector, remaining are the your 60-degree phase shifted vector. As you can see in this diagram, how the V1 is defined. The V1 is defined 1, 0, 0. It means the A phase upper device is on of the inverter, and B and C phases lower device are on. And the last two vectors 0 and 7 are the 0, 0 vector, as you can see in this complete let's say the holograph, flux holograph and voltage vector. And these typically matrix converter based, of course you can call it the direct torque control. So we have a position, and from position to speed, then we have a speed control, get the torque reference T star, and from actual speed we get the flux reference. also. And then from two currents and position, we are able to rotor position, we are able to get a estimated torque and flux. Then we go to level torque and 3 level flux. With the position, we go to table optimal switching to which give the directly space factor modulation to the Matrix converter. Now coming to sensorless vector control of the synchronous reluctance motor drive. So for sensorless control, the estimation of position or speed becomes inevitable, and the speed can be estimated by following relation: omega equal to, in bracket, lambda alpha e beta minus lambda beta e alpha divided by lambda square, and lambda square equal to lambda is alpha square plus lambda beta square, and angle gamma is tan inverse lambda beta upon lambda alpha, and instead of flux is estimated from the motor back EMF by using integration as E equal to d lambda upon dt, and motor back EMF can be calculated from E equal to Vs minus R Rs Is, and this is typically your sensorless control in typically in wayside drive for vector control. So what we do here in sensorless, we are sensing the voltage and current from which we are getting a estimation position of speed both here, and then we have a reference speed and this estimated speed. We have a speed control give the torque, and from actual speed we get the flux. Then we go to vector controller to give a IDIQ reference, and we have a typically IDIQ from Clark transformation and Park transformation. So we have a current controller in typically in DQ axis that give the VDQ star, and using the Park transformation we get V alpha beta, and using a typically the inverse Clark we get the VAB VBC for controlling the your voltage source inverter pad or in synchronous reluctance motor drive. And this is the case of your current controller. So here also we sense the voltage and current and estimate the position and the speed, and then we have a speed controller with reference speed and actual speed. We get the flux reference lambda star, and from vector control we get IDIQ references, and this IDIQ reference we convert from Clark inverse Park transformation IAI-BIC, and we have a feedback current IAI-BIC. We give the current controller to the gating signal for the voltage source inverter. And this is typically matrix converter based sensorless control. So again, we sense the voltage and current of the motor, from which we estimate the position and speed, and we have a speed controller give the torque reference T star, and then the from actual speed the flux linkage reference lambda, and then from vector control we get IDIQ references, and we have estimated IDIQ from Clark and malformation, and then using current control we get VDVQ reference, and from inverse Park we get V alpha beta reference, and Clark transformation we get a 3-phase reference voltage to calculate the duty cycle of matrix converter feeding the synchronous reluctance motor drive. Now coming to topology of sensorless director control synchronous reluctance motor drive. This is typically a diagram of your voltage source inverter pad. So here again battery operated, so we have a sensing voltage and current and getting a position, then speed, then we have a speed controller with the reference speed and flux from actual speed the flux reference, and then we have a torque and flux estimator from voltage and current, and then we have two level torque and 3 level flux. So that gives the error, and along with the position we get the go to table of optimum switching to get your switching vector for space factor modulation feeding switching the your voltage source inverter feeding the your synchronous reluctance motor. Similarly for matrix converter, so we have here the sensing voltage and current, and from which we are getting a position estimation from position to speed, and with reference speed comparison we get the speed to give to speed control get a reference torque T star, then actual speed we get the flux reference lambda star, and then we have estimate from estimator we get a flux linkage and torque, and then after that we have a two-stage 2-level torque control and 3-level flux control, and with that and your position sector we go for table optimum switching for giving a signal for your space factor based modulation for matrix converter driving your synchronous reluctance motor. So now coming here, the typically how it is active flux based model sensorless control with the voltage and flux stator flux observer as shown in the diagram. So the active flux was born by generalizing the modifying the virtual PM flux in the interior magnetic synchronous and the extract EMF models to the all AC machine. So the active flux phi AD for the synchronous reluctance motor here along with the D axis of the rotor, typically LD/LQ, is obtained from the observer stator phi D alpha equal to phi S minus LDIS, and this observer process flux is not current, but phi AD is aligned to the D axis irrespective of the load, speed and voltage waveform. where the integral set is reduced by the PI controller loop in the voltage and current model of a state observer as is shown in the diagram. And this is typically the complete active flux based sensorless field onto control. So here also we are sensing the typically the current, and then we have a filters and then estimator. So it goes with the speed control of the torque producing component. Then we have flux producing component goes to the with the PI control. We get VDBQ, the cross coupling, and then it again by inverse transformation we get the your typically the voltage impacts, and we have a vector. So we go for space vector modulation. So here you can see how the photograph of traveling voltage vector injection at standard still for synchronous. So injecting say the traveling voltage vectors in the rotor coordinates at zero speed yields a circular photograph for the alpha beta state flux vector component phi s alpha phi s beta to the elliptical current photograph alpha beta, but to fixed axis AC signal for actual flux active flux at injecting frequency. The position of this vector is still the rotor position even at standard still. So magnetic axis is thus described decifered, and PM polarity requires two voltage plus voltage vector along with the estimated rotor position at standard still and by measuring the larger current peak after a given time. So here is a PLL based position and speed observer based PID input and motion control as shown in the diagram how the position and speed are estimated. So phase loop additional observer that uses the motion equation is required to condition theta PID to obtain the cleaner rotor position estimation theta ER, and as the bonus the rotor speed estimation omega r, and the motion equation give the state observer some robustness to the torque per derivation during speed tangent. And this is the magnetization curve of 157 watt 4-pole 1500 synchronous motor of D axis and Q axis. How with the D Q axis the fluxes of D and Q axis are varying, of course, for different level of your IDIQ. And this is the test result of active flux based sensorless control of synchronous from zero speed of operation. You can see here the speed, phase current and position as well as the torque. So zero speed operation at zero with the plus 1 Newton meter torque per derivation, speed, phase current, position, etc. and torque. So now coming to V/F control of PM assisted synchronous with the stabilizing loop. So for pumps or compressor like loads and EG, throw a bit hesitant, start without initial rotor position estimation is a functional asset, and simplify control with a large enough speed control range in that coderless implementation may suffix in such applications. So this is how the simple the open loop V/F control was improved, but for more stability and wider range by adding stabilizing loop, still V/F control does not have a speed closed loop or DQ or ABC state current regulator, which is a plus in the licensing demand drive now serve as a index motor advanced V/F drive, but such V/F drive should have the MTPA conditions embedded and provide the wide constant power speed range at least for the redundancy. Now going V/F PM system, this loop. So such V/F modifying system on the active flux model was developed in characteristic by a stator flux combined with VI model closed loop observer with the active flux that phi AD equal to phi S minus L is into IS with the PM in DXS LDLQ, and phi AD equal to phi PM plus LD minus LQ into ID, and phi D equal to LDIQ plus phi PMD. And for MTPA condition, is kept IS is kept constant with IDL lesser than 0 and instead of IDQ greater than 0. So IDI star equal to minus IS in under root your phi D alpha is phi D divided by 2 into phi D A minus the phi MD and phi MP. So phi D A star equal to phi PMD plus LD IDI. And this is typically V/F control assisted PM assisted stabilizing. So V/F control is the voltage reference and the current structure. So this is typically how the you can say the frequency, and you are getting the position, speed, and voltage corresponding for this V/F scalar control, and that how the reference generation of voltage and how the your DXS current and how the flux estimation, so and how it goes into the loop with the back of this control of this active flux observer for this your space vector modulation control motor. And the steady state performance at 1 RPM, speed 0.5 Newton meter, torque per turbation, and the operation 1 speed of 1 RPM operation with 0.5 Newton torque per turbation. With first is the speed, then the phase currents, and then position error and torque. And this is the performance at 1500 RPM, speed reversal, tangent with 1 Newton meter, torque per turbation, how it looks like, and the reversal tangent with 1 Newton meter per turbation with the speed, phase currents, and position error and torque. And this is the performance at 3000 RPM, speed reversal tangent, as you can see, and plus 3000 speed reversal and speed, position error, and torque. And this is the EVI control to stabilize the at 5 RPM for IABC and speed and delta V. And this is the PM RSM acceleration to 1400 RPM and load proportional to speed, 50% by V by F control, 3-phase currents, then the speed, and then the theta rotor position and torque. And this is the diagram simplified wide speed field oriented control sensor as PM assisted. So we are sensing voltage and DC voltage and current, from which we are getting speed and flux error. And then of course we are going from torque characteristic, speed, reference speed, actual speed, then with PI and anti wind up we get reference torque, we limit it, and then we are getting from history current your torque error, and then we get the LDLQ, IDIQ star reference current, and then feedback current with the your DQ current regulator, then we get VD star, VQ star, then from this we get voltage and angle with the for the transformation, and we get P alpha beta for space factor modulated your BSI. And these are the sensor as opposed to PM at 5 RPM, what are the 3-phase currents and how the speed. And then this is the PM acceleration at no load at 1400 RPM with 50% load applied at 5.1 second, as you can see here. Sensorless field under control with the 3-phase current, speed and torque. And these are typically experimental platform for active flux estimation, low speed sensorless control of this axially limited synchronous reluctance. Now coming to the case study, the synchronous reluctance motor drive for solar PV array fed water pumping. So here we can divide a classification of it. So solar array fed water, we have a standalone solar PV water pumping system, standalone or 2-stage variation, and the standalone single stage power. And then the grid connected solar PV, that we have a single phase grid connected for water pumping with the universal power flow, bidirectional power flow. Then there's a 2-stage and single stage. Similarly for another single stage and 2-stage. Then another is like your grid connected 3-phase grid connected solar PV array fed SRM type for water pumping with unidirectional power flow, bidirectional power flow, the 2-stage and double stage in all cases. So it becomes like a typically kind of 8 cases in solar pumping. So taking a first standalone 2-stage solar pumping drive, so we have a PV array with the boost converter, and then feeding to DC link, and then we have a synchronous reluctance motor. So DC link, this boost converter is essential for maximum power tracking, and the DC link voltage is controlled by controlling the speed of typically of synchronous reluctance motor, and the speed is decided by how much power is fed to the motor, like for driving the water pump. So these are the specification of the motor. I mean typically 4 kilowatt motor taken with the 3000 RPM. I mean here you can see all the parameters of this machine. And then for design calculation, DC link voltage we set 600, duty cycle pumps and inductance comes typically around 5 millihenry pushed inductor. And then the DC link capacitors comes around 2300, 500 applying this relation. The drop of inheritance occurs when I reduce, resulting in a higher value of DC capacitor. Therefore, to ensure performance, the motor pumps somewhat higher value of 2300, 550 microfarad is chosen. So similarly, we select the rating of the IGBT of voltage. So VSI equal to VDC into KI with the safety factor 840 volt and current rating also say current with the safety factor, and we can select the IGBT of 900 volt with 9 ampere. Finally, VSI of 8.5 VA. Now coming to design of water pump, the characteristic of water pump are obtained using a affinity law. Affinity law states that the discharge rate is directly proportional to the speed and head is directly proportional to the square speed. So flow rate is Q equal to alpha 1 omega minus alpha 2, and head is equal to B1 omega square minus B2 omega. So mechanical power required for the pump is proportional to the product of head discharge rate and depends on the opening closing of discharge value, and this relation is represented by following a P mechanical equal to alpha omega square minus B omega square plus C omega, and at higher speed lower order terms are neglected, so P mechanical is alpha omega cube, and A equal to P mechanical upon omega square. That value comes 1.29 to n power minus 4 watt per radian per cent cube. So now coming to control of system, for of course boost converter we do maximum power tracking, and then we control your synchronous motor, either vector control or director control. So this is the incremental conductance, maximum conductance, power, maximum power tracking. How we really go with we decide on whether we have to increase the duty cycle or decrease the duty cycle according on left side or right side. And this is speed sensorless control of your D-axis current control. So we have sensing of 3-phase current, and from 3-phase current we have of course the estimate from this diagram for MPPT. We get the power, and of course from that we get the duty cycle for maximum power for boost converter. But for this power we use for speed reference calculation also. And then we have a DC link voltage control, as you see, reference voltage and feedback DC link voltage, that gives the negative, because that should reduce the power to regular. Otherwise, if motor draws more power, then DC link voltage reduces. So it means you should reduce typically the reference speed so that the DC link voltage is maintained. And difference of two, we take a reference speed, then we have estimated speed, go to speed control to decide the torque, and from this torque and from ID we are able to get the IQ. So we have ID IQ, and from position estimated we get Park inverse transformation to get 3-phase hysteresis current, and with sense current we give the gate signal. So this is vector control. Of course, your synchronous reference motor IQ, the DX. And this is the typically speed sensorless control, how we are getting a speed estimation from DC link voltage switching function. We get the typically the here the and the 3-phase current, so we get it from typically the flux, and then typically from flux we are able to get the hysteresis current, and we are able to get typically from this the position and speed. Finally we are able to get speed also and along with position. And this is another method, your D-axis inductance mode calculation. So we also estimate the D-axis so that the tuning of the estimation is not there. So D-axis inductance is also estimated by this technique, as you can see in detail. So coming to this presentation, vector control technique is adopted by controlling the synchronous, and control is two-part: estimation of reference speed. We talk about have a reference speed as it is shown with the DC link voltage controller. We have a one term, another is from HL power, that is positive, and negative from DC link voltage control. We have a reference speed, and then we have a feedback estimated speed. We get the typically the DC link voltage control. So we get the reference speed from PA minus W1 minus your WA upon WB minus W. So now coming to vector control, the sense speed is compared with the reference speed, omega star and G delta pass through PI control to get reference torque. So in equation T star n equal to E n minus plus K omega E n minus plus K I 1, and this torque reference is used to calculate the D Q axis reference current as given here. ID star equal to under root 2 T absolute LQ upon 3P LD minus LQ LD. IQ star equal to 4 torque absolute divided by 3P LD minus LQ ID. The reference stator current are obtained by the DQ axis current using path transformation, and that we have hysteresis current control. So this is experimental setup on which this, and this is the MPPT performance at your 1000 watt per meter square and watt of the solar emulator. And these are the starting performance of the synchronous motor for vector control drive. As you can see how it really goes, and then the self-safe starting mode, and then these are the steady state performance of solar PV, including you have a PV voltage, PV current, then PV power, DC link voltage, 3-phase current, speed, then you have flux estimation, phi alpha, phi beta, net flux, then the position, and then you have a typically again the torque estimated, flux estimated, hysteresis current and speed, and then the flux, reference speed, estimated speed, and the LD value estimated there. And these are of course all the parameters: speed, power, when the solar insolation level reduces, how the speed and currents, all those parameters, and when your solar insolation increase, how the performance of this. The another is sensorless control for adaptive your D-axis current control method. So from maximum power tracking, we convert all the boost converter, and from this we get the reference, and we have a DC link voltage control. Then we get a torque reference. Then with the LD estimated, we go for estimation of the IQ also, and then from this typically from your IQ and ID and 3-phase current you're able to get a position and speed estimation too. And this is the power, typically the maximum power tracking, typically for your solar emulator at 1500 watt per square. And this is typically the starting performance, control starting performance of typically with then MPPT enabled performance. Initially for starting, we don't have an MPPT, so we enable MPPT once the motor is started. Then all the parameters which you are having LD estimation, then typically your ID and flux linkage, then the steady state performance of all, including your actual current, flux linkage, your flux link estimated, and for all these parameters doing when solar insolation reduces as well as typically increases. Then coming as standalone single stage PV fed switch reluctance motor drive for water pumping. So here we have a PV array directly feeding the typically for voltage source inverter with the power control. So here the DC link voltage for MPPT is decided by the inverter control for controlling the speed of the motor. And if the power is more, the motor will run a higher speed. If power is less, it will run on lower speed. This is the control that we get the reference again speed from DC link voltage control, which we decide for reference as a from MPPT. And since MPPT have a DC voltage control, give a one component of reference speed, another comes from power estimation, and then we have a reference speed with estimated speed, which we are estimating in lower block. And then it goes to the speed control to get IQ, and then we have ID from here with the using the Park inverse and transformation we get IB star. Then we have a sense current to give a current controller code. So this is even a lower block we have estimation of speed and position both. And this is the MPPT performance at 1000 watt and 500 watt per square. And this is the starting performance. Of course, during starting we have open loop starting, then we have MPPT sensorless control, and then you can say flux estimation 5D 5Q, how it is a complete circle. So you don't have three phase currents, and you have a typically the 5D 5Q as well as 5 and the position estimation. And then all these performance during solar insolation decrease and in solar insolation increase. And this is the speed sensorless control of switch reluctance, the adaptive T-axis control. So similar control, we have a DC link voltage control. DC link voltage we get from typically from PV power, VDC star. Then DC link voltage give a negative component of reference speed by we get from power the positive component. Then we have a estimated speed. So speed control give the torque, and from LD we have all calculation ID IQ, and then typically estimated speed we are able to get three phase current, and sense current we have a gating signal. And this is the performance for typically for MPPT performance of 5500 watt per square. And this is the starting performance. Then switching to MPPT enable, at different solar insolation level is sensorless control. And then this is performance during change of solar insolation, decrease and increase solar insolation. So now there is single page grid interface unidirectional two-stage PV array fed synchronous reluctance motor drive. So we have a PV array with the boost converter on DC link, and we have a boost converter, PFC boost converter with single page grid to on the DC link. So what we can take, whatever power is available from PV, we take it. Remaining power comes from single page grid through boost converter with the power factor correction, and we are able to get uninterrupted water pumping from this synchronous reluctance motor drive. So for unidirectional power flow, other things we have already. So we control the DC link voltage here with the voltage controller. So we get the amplitude of current, multiply the template, we get the reference supply current of our inductor current, and we have sense current. So from this PI controller, we get the reference voltage, and comparing with the SHA-2, we get the gating signal for the boost converter voltage, typically voltage. So now operating mode 1 is the mode which comes into the operation when the grid supply is not available. Only PV power available. Mode 2 is when there is no power or negative power available from solar PV array, only grid is feeding, and when the solar PV power and grid supply both are there. And this is typically the parameters of the system. And this is the design, the inductance calculation of the grid side. It comes 4 millihenry with the proper relation. And this is the MPPT performance for 1500 watt per meter square. And this is the starting performance. Typically only with the solar and the all parameter estimated here. Then we have a solar insolation change for mode 1, and then we have a typically starting with we have a grid also, we have a solar also, So only with the grid how we are starting and how we are able to get TAD of only 2.5% with power factor unity on the grid pipe from boost converter and all parameter of the grid as well as motor parameter. And these are solar insolation and power factor typically on different level of power around like. And then when the solar insolation changes, decreases, grid current increases obviously, and when solar insolation typically increases, the grid current reduces, as you can see in all the. Now taking another typical topology, single stage solar PV system. So we have a direct PV, then DC link voltage is controlled by the again by synchronous this inverter fed drive, and we take remaining power from the your single phase grid. So here also mode 1, the mode comes to operation when grid supply is not available, only PV power is available, and mode 2 when there is a no power or negligible power available from the solar PV array, and mode 3 is when the solar PV power and grid supply both are available. And this is the parameter of the motor, and this is MPPT performance 1000 watt and 500 watt meter square, and this is the performance starting, safe starting, and then we go for MPPT enabled performance with the position also only in mode 1 when solar is available, and similar performance with change of solar insolation. Then the second mode when grid is available, so you can see grid current increases as we only grid is available, so grid current increases as the motor is started, and we get the TAD only. Power factor unit 99 and TAD of current is only 2.5% and all the performance parameters. Then the mode 3 when the both solar and PV are available, so here also we take less power from the grid is power factor unity, and TAD of supply 3.6% because of low power. And then the typically starting, you can clearly see, if solar insolation reduces, the grid current comes more, and when solar insolation increases, grid current also reduces like that. There is another topology which we have a solar with the boost converter, and we have a single phase supply with the edge bridge or fully controlled converter. So we can say if extra power is there, it can go to the grid, while pumping is not required, and also it can go to the grid. Or you can, when solar insolation power is less, so you can take power from the grid, or even if solar is not there, then also you can run the pump undetectable like. So that is of course the DC link voltage control, how you are getting for VSI control, DC link voltage control and power, you get the typical reference DC current, and then you have template, you get the supply current, and then you have current control. So it's automatically will feed the power to the grid if you don't really run the pump or extra power is there by controlling the DC link voltage. So here also mode 3, mode comes only when the grid supply is not available, only PV power. Mode 2 when there is no power or negligible power available from PV, and mode 3 only grid is operating and solar PV power and grid supply both are available. Mode 4 when solar PV array is more than the required rating of the water pumping, this mode comes into action, feed the extra power to the grid. And these are the parameters of the system, and this is the performance. So you can just see here, so because rating of this is there, so we have at MPPT 500, but in higher power we have to operate in, because solar level is high, so pump cannot operate on much than rated. And these are performance for starting, and then safe starting, and then we go for MPPT performance. Similarly for in mode 1 extra power is there, then how it really goes for. And then second mode with the grid, and both are there, so TAD of grid is 1.6% with the almost 0.99 power factor, but power comes from the grid. In mode 2 there is no PV array power, and then the third mode we have a PV also as well as grid, so whatever power comes from the grid have a TAD 3.9% less power coming from the grid, and both sources. And then certainly you can see when solar insolation reduces, grid current increases, when solar insolation increases, grid current also reduces. And then you can see at this power also we get TAD almost, we are able to feed it in mode 4 the power to the grid, as you can see 1.6 kilowatt power is fed to the grid from and then the performance in different modes, like changing from one mode to another mode like. Then this is another typically single stage solar, so DC link voltage will be varying according to MPPT of the solar PV array, and then single phase VSI, all 4 mode will be there of course in required like. This mode comes only when grid supply is not, only solar is there. Second case only non-grid is only there, PV is not there. When the third is both are there, and fifth is then power generator is more than the what required for water pumping, or pump is not operating. And these are the motor parameters. So first mode, because power is only solar power is more, then you have to go up 50 mode to run at fully speed this pump, and then soft starting, typically with, and then the operation at different PV panel, but the speed of the motor is maintained constant like. And then the only second mode with the grid only, so you can say TAD of 2.2%, and power factor 0.98, and then when both are there, this is mode third. You have solar as well as grid. So here also little power is down from the grid, and TAD is 3.8%, and the solar variation is there. In mode 4, when you are feeding power to the grid, I mean, like, so here you can see 1.6 kilowatt power is fed to the grid, I mean, like, and the operation varying from one zone to another zone. Another case is when you have a push converter with the solar and you have a 3-phase grid with the VSI, and this certainly you can call it, I mean, it's a roof type of application, so you can feed if extra power is there to the grid, as well as you can take power from the grid in the night also. So typically night metering can affect here also, or so both can feed the source. Only solar can feed, only grid can feed, and solar and these can feed, and pump is not running, or you have a typically more solar power, it can go to the grid. So this is the control here again for this. So we have a motor control in vector control mode, as well as the MPPT control from the boost converter, and all 4 modes are there. Then only the solar is available, only grid is available, and both are available. And when not pumping, I mean, power is more than pumping, so it goes to the grid. This is the parameter. So you have a first case when solar rating is more, so you run at the full, but if insolation is more, then you are not able to absorb whole power by the pump. So it's run off MPT mode. So starting different modes in mode 1, and mode 2 only grid is operating. So you can say safe starting of the motor. We say this, the motor is more safe. In this case, you are operating always with the inverter, and quality of current, I mean, supply TAT is 1.7%, and power factor is unity. And here the mode 3, when solar as well as grid power both are feeding here, and TAT power factor is close to unity. And of course, you're sharing that at different solar insolation. And mode 4, when you are feeding the power to the grid of 3.79 kilowatt, pumping is not done, I mean, and you are having current out of the page with the voltage. And then of course changing the mode from one mode to another mode. Another case is single stage of solar, and then 3-phase grid with the bidirectional converter. So here also all 4 modes are there. Mode 1 is in operation when grid supply is not available, only PV is feeding. Second case, no solar, only grid is there. Third case is only both are available, PV as well as solar power. And when fourth is when you have a solar power generation more than the pump requirement, so power is fed to the grid. And these are the parameters of the model. So first case when solar is there, but you have only 4 MPPT and then lesser power, and when more power, you have to run off MPPT to run at steady speed this pump. Then of course soft is starting in this mode 1 and varying off mode. Then only grid is there, so safe starting from the grid, and variable frequency drive, and TAD of supply current is also 1.7%. Power factor is almost in unity, all estimation of position. So this is the third mode when power is coming from PV as well as from the grid, and power quality is improved on the grid with the unity power factor, and varying mode from one to another. And the fourth mode is when power is fed to the grid. We are feeding typically TAD of supply current is still 3.1 with power factor close to unity, and 1.53 kilowatt power is fed on the grid after feeding the pump, and the different modes of it. Now coming to case study 2 with the speed sensorless synchronous reluctance motor drive for electric vehicle application. So here you can just see the tractive upward required for thrust vehicle is FTR equal to FAD plus FROL plus FL plus FLE and FW. Here with the driving cycle we have a velocity reference and velocity of wheel, then velocity regulator, we get the FTR, and then we get the different other components also. This we get total force, velocity, and then we convert into reference speed and the torque for speed control. And this is the typically how the force and velocity and torque is there. And this is typically the case when we are feeding mainly from the boost converter from the battery. So battery we are keeping low voltage, little lower voltage and DC link, and the PV we are having boost converter on DC link itself, and we are running this typically a, you can say 3-wheeler from 3-phase VSI synchronous reluctance motor drive. And this is the control. We have a reference speed, actual speed. We are sensing the, of course, the DC link voltage, and we are typically sensing the 2 currents. So getting a typically from DC link and 2 currents, we are able to get position and speed, and then speed reference. We have speed control, getting torque, and then from current we get a IDIQ from this. With the position we get 3-phase reference current, feedback current, get the getting signal for the inverter. And of course from boost converter we do MPPT feeding on DC link. So if excess power is there, it charges the battery, and if less power is there, so of course feeds along less power taking from the battery to the inverter. these are the typically control. Developed torque is T equal to 3 by 2 P by 2 lambda I star. That becomes T equal to 3 by 2 P by 2 lambda D IQ minus lambda Q ID. And for speed control of synchronous and indirect field under control is chosen. The reference torque is, which depends on the speed controller. So, is speed torque reference is estimated from speed controller. The reference ID IQ are calculated from these relation ID star under root 4Tk upon 3P LD minus LQ and IQ star is ID star upon K into sine of T star. And this is the typically phasor diagram. So, stator flux components is estimated from the measured direct and QRJ resistor voltage and current. So, lambda S alpha equal to integration of Vs plus minus RS I alpha dt, and lambda S beta is integration of VSB minus RS I beta dt. The stator flux linkage space vector is obtained with rho S tan inverse lambda SB upon lambda and omega RS equal to d theta RS upon dt equal to dps upon d delta S upon dt minus d upon dt equal to omega S minus omega d. Omega S equal to d rho ps upon dt, and getting from this relation we get this experimental setup for this system. And these are the performance. You can see estimated position as well as speed and battery current DC link voltage, and then the current motor current here and estimated speed, and then you have a typically your D and Q axis flux, battery current and the position, and the starting you have a typically battery current, speed as well as the current safe starting, and then your change of speed, typically in different modes, like, and then the solar performance for MPPT. The another case is, of course, we use the directly DC link voltage, battery on directly DC link, and solar boost converter. And the control here, how really the push, again vector control, sensorless vector control for single vector motor with boost converter, typically operating with charging a battery. So these are the equation. Of course, here we use the vector flux linkage component estimated phi alpha beta. Then from we use the typically filters for flux estimation here, and we get adaptive flux adaptation. So here typically for solar sizing, due to space constraint, the roof of PV solar PV is limited to 600 watt, and the VOC of panel is chosen 400 volt into account the signal with the current of 0.15, and then the typically 330 volt the boost converter. And duty cycle calculation as well, inductance calculation 6 million, capacitance calculation 500 micro. This is the performance during typically the acceleration, typically, and the acceleration, how really, and normally steady state running all the performance. And then here is starting for reference speed, then the speed change, reference speed change. So these are steady state performance corresponding to different speeds and different parameters. Then the dynamic performance from speed change from 800 to 1000, 1800 to 1200 and to 800 RPM. And the performance again for dynamics for half the load on the shaft, and then you can call it comparison of your filters technique for the estimation of position. Then the stability analysis of this complete drive system with the body plots that it stays stable, and then these are the parameters of the system. Then we have again boost converter with solar and the battery with the buck boost converter, typically a bidirectional DC-DC converter. And then the control here with the MPPT control as well as the motor control dynamics here with the sensorless vector control, and then the converter control typically. So here is the battery current control. So while VDC is in boost mode from acceleration phase, and the boost battery is supplying the power to as per required on the wheel. Both push and buck modes have been two modes of operation, which having either switch X in mode or SY or SZ mode. The switching pulses to the switches are mentioned in control loop, which consists of one voltage regulator having VDC as reference voltage and current controller reference battery current obtained as the output of the voltage control. And this is the estimation of the flux, and the flux expressed as a typical DC component, and then with the filter we remove the DC component other. These are the filter equation, and this is the performance. Of course, during typically acceleration, deacceleration with the regenerative wave, and during starting typically, and the different parameters. Then we have again the boost converter with the typically, and battery also with boost converter, but the solar is on the battery and then controlling. So here also we use the vector control and the boost converter with the solar, and the control again the flux estimation typically, and the position and speed estimation. Then the typically extracting the position and speed from using filters, and the performance typically under different like starting, then running, and regeneration position estimation. And then the typically the comparison of the your sliding mode controller and adaptive sliding mode controller. Then another case typically again with the boost converter with the solar and the battery on the direct with the your typically the configuration, and then here again we have a battery control for speed control of this complete system, and then the flux estimation with the filters, then the starting performance for sensorless control, and typically then switching for finally, and the position estimation, current, voltage, all the signals for doing estimation, and the performance during speed change from 1400 to 1600 to 1800 rpm. Then dynamics, all the parameters, and then the flow graph typically of trajectory of the flux linkage and position estimation. Another case is that we have a typically from the power charging from the grid as well as from the solar, the battery, and these are control for again motor control, the boost converter control and grid converter control, and the estimation of the flux and for motor control as well as the speed and position estimation and flux estimation, diesel voltage control. And these are the typical equation for estimation, speed and position, the power filter and the performance simulated performance for this purpose, and the position in different operating conditions, then the current, grid voltage, and total harmonic distortion of grid current. Then the typically the comparison of sliding mode controller controller at different speed. Now coming to the typically the solved numerical problems. So coming to example 1, a 3-phase voltage source inverter, PAD 3-phase 50 volt line, 50 hertz for pole star connected synchronous reluctance motor has a LD equal to 10.5 millihenry, LQ equal to 1.91, and negligible resistance. This motor is driving a fan load. The torque is proportional to the speed, which is 7 Newton meter at 3000 rpm, and the speed of the motor is controlled using an indirect vector control scheme through pendulum voltage source inverter. The motor is controlled with a constant flux below base speed and constant rated voltage above base speed. Calculate the reference TQ current of the stator current. Component of stator current at starting, if starting torque is required rated torque. So here is your solution. ID is given here, your typically 10.5 millihenry, and LQ is given your 1.91 millihenry, and motor torque is calculated 3 by 2 V by 2 and D minus LQ ID IQ. The torque is given 7 Newton. ID comes here typically as a function of 271.5, putting a value. So we get the typically the speed, and substituting a value we are able to get here IQ equal to 23.7, and substituting that we get ID equal to 11.6. So coming to example 2, a 3-phase VSI at 3-phase 50 volt 50 hertz for pole star connected synchronous reluctance motor has LD equal to 10.5, LQ equal to 1.9, negligible resistance. This motor is having a fan load where the torque is proportional to 7 Newton meter at 3000 rpm. Speed of the motor is controlled using indirect vector control scheme through pendulum VSI. The motor is controlled with a constant flux below the base speed and constant rated voltage above base speed. To calculate the reference DQ component of stator current, and you can see at half the rated speed and 1/4 of the rated. So this is the solution. Reference DQ component of stator at the half the end. So LD is given 10.5 millihenry and LQ is 1.91 millihenry, and from the torque 3 by 2 P by 2 D minus LQ ID IQ, the torque is 1/4, that is T rate of 1.75 Newton meter. From this relation we are able to get ID equal to 69.9 IQ, and from flux from rate here putting the value we are able to get a equation in IQ fourth order, get the fourth root, and out of 4 root we are able to get IQ 5.1 ampere and ID equal to 12.34 ampere. Coming to example 3, a 3-phase VSI platform 50 volt line, 50 hertz 4 pole star connected synchronous reluctance motor has LD equal to 10.5, LQ equal to 1.91, and negligible resistance. The motor is driving a fan load where the torque is proportional to speed, and which is 7 Newton meter 3000. The speed of the motor is controlled using indirect vector control scheme through pendulum voltage source inverter. The motor is controlled constant flux below base and constant torque. The speed is required to raise 0.75 times the rated speed. Calculate the DQ component of stator frequency. So if the rotor speed is equal 0.75, the rotor calculate the DQ component. So LD is 10.5 millihenry, LQ is 1.91. So putting the torque equation T equal to 3 by 2 P by 2 LD minus LQ ID IQ. So torque here is 0.75, that is 5.2925 Newton meter. So ID we get 203.71 IQ, and from flux equation we are able to get voltage, and putting this in equation we get order IQ in fourth order. So we get the ID equal IQ equal to 17 ampere and ID equal to from this 3.09 ampere. Coming to example for 3-phase VSI, we had 3-phase 415 50 Hz 10 pole star connected synchronous reluctance motor, XD equal to 25 ohm, X equal to 5 ohm, and negligible resistance. The motor is driving a load which torque is proportional to speed is 10 Newton meter at 600 rpm. The V by F is maintained constant at the rated value. If inverter frequency 25 Hz, calculate the input voltage, armature current, and torque angle, and the pull-out torque. The solution is V by F control is U, the voltage proportional to frequency. So V1 upon V2 equal to F1 upon 2. We get the V2 equal to 207.5 volt line, and pull-out torque from then VL square upon 2 omega 1 upon XD minus L. So it comes the value 219.25 Newton meter. And coming to the part C, the torque is given 10 Newton at 600 rpm, so at 25 Hz, the speed is 300 rpm and torque is 300, 5 Newton meter, and torque maximum to sine 2 delta. So delta we get clearly 0.653 radian. So now IQ is V is sine delta upon LQ. So putting the value we get 0.546, and ID comes 9.5, and IA comes under root ID square IQ 9.6. Coming to example 5, a 3-phase 415 50 Hz 4 synchronous motor has the following parameter: magnetizing inductance along with D axis 8 millihenry, magnetizing Q axis 1.5 millihenry, and the leakage inductance 2 millihenry. Calculate the maximum torque developed by the motor if it is operating at a rated speed and power factor in this condition. So LDG LDL plus L1S, that is 10 millihenry, LQ is LDQF L 3.5 millihenry, and torque 3 P square upon 2 omega. So it comes 324.07 Newton meter, and 10 phi XD plus XQ upon XD comes 2.07, and pi is 64 point, and power factor is 0.433. Coming to example 6, a 3-phase 4-pole 50 Hz 4-pole star connected synchronous reluctance motor has a direct reduction quantity 8 ohm and 2 ohm respective for load torque 18 Newton, and the load angle, line current, and power factor neglect the armature resistance. So here a frequency is given 50 Hz, pole is 4, T equal to 18 Newton, XD 8 ohm, X ohm. The voltage is 400 by 3, 30.5, omega is equal to 15 radian. So T omega is your 12,537 watt. So here torque equal to 3 by omega V square X minus sine 2 delta. So delta comes 12.38, and load angle comes and ID comes V cos alpha upon XD 28.17, and IQ comes V sin alpha upon XD 24.76, and line current is under root ID square equal 37.53. Power factor is 3 VI equals. So here power factor comes 0.4833. Coming example 7, a electric car has a open circuit voltage of 180 volt. Its corner speed of 3000 rpm. The supply from a PWM inverter with maximum voltage 210. Find the maximum speed at which the maximum current can be supplied by to the motor. So neglect armature resistance, other losses. PMS switcher synchronous motor has been used to drive this car. So here is the locus of current. At corner point V is equal to 180. So omega C is 3002 314. So ratio between this V and C is K equal to omega B upon omega C. So where here VC upon V0 minus under root E square. Putting the value, this omega B K comes 1.76759, and omega C K 555.03, and maximum speed is 16 to omega B upon 5, that is 55,300 rpm. So coming to example A, a VSI fed 3-phase 230 volt 50 Hz 6-pole star connected synchronous reluctance motor has X equal to 50 ohm and X equal to 5 ohm, and negligible resistance. This motor is driving an e-vehicle. Its torque is proportional to the speed square, and it's 10 Newton meter and 15 rpm. The speed of the motor is controlled using the indirect vector control scheme through below voltage source inverter. The motor is controlled with a constant flux. Below base is constant rated voltage, above the base is speed. So calculate the reference DQ component of starting current at starting if starting torque is required rated torque for best transient response. So coming to solution, XD 50 ohm, X equal to 5 ohm, LD equal to 0.159 Henry per phase, LQ equal to 0.1. So motor torque is 3 by 2 P by 2 LD minus LQ ID T 10 Newton meter, I 15.5 to IQ. So for putting a best transient response, ID upon IQ equal to LD, LQ upon LD, that is 0.1. By solving this, we get IQ 12.45 and D equal to 1.240. Coming to example 9, a VSI PET 3-phase 230 volt 50 Hz 6 pole star conversion converting motor has XT equal to 50 ohm, X equal to 5 ohm and negligible RS. This motor is driving a vehicle which is torque is equal to the speed square and 10 meter at 15 rpm. The speed of the motor is controlled using indirect vector control scheme through pedal motor source inverter. The motor is controlled with a constant flux below base speed and constant rate of base speed. Calculate the reference DQ component of current and stator frequency at half the rated torque and 1/4 of the rated maximum. So coming to solution, 1/4 of the rated torque is your ID upon 3.88 IQ for maximum power factor. ID upon IQ under root LD upon LQ, that is 0.3, and from 1 to IQ equal to 1.107 and ID equal to 3.505. Stator frequency at half the rated torque is at 25 Hz. Coming to example 10, a pedal scooter driven by a synchronous motor has the following data: rated speed 1000 rpm, pole pair 3, LD 88 millihenry, LQ equal to 24 millihenry, ID equal to 2.3, LQ equal to 24, RS equal to 1.74 millihenry, J equal to 0.15 kg meter, V0 equal to 112. Calculate the maximum torque, maximum ideal acceleration, time required to reach, and the base speed under the peak torque and no load. Coming to solution, peak torque is T equal to 3/2 P by 2 LD minus LQ into lambda square 2 LD LQ. So putting it from our lambda under LD ID square plus LQ square, that is 0.21 Weber, and T equal to 3.3 Newton meter, and maximum acceleration is T upon J, that comes 191.08, and time required to reach the base speed T equal to omega B upon P lambda max, it comes 0.18 millisecond. These are the references which are used to typically developing this material, this lecture, and thank you.